so let's take a look at carrying capacity. And by the end of the presentation, you should be able to determine how a population changes over time, what the difference is between immigration, emigration, and you should already understand that from our discussions on Hardy-Weinberg. And what is exponential versus logarithmic growth? What do the curves look like? What is carrying capacity, and what determines that capacity? You should be able to analyze population data and graphs and determine where the carrying capacity is on a graph, and you should be able to understand what all of it means. How do you put it together and answer questions concerning carrying capacity? So we're taking a look at a big idea, and the big idea is population size and how it changes over time, and you have to think about what determines population size. So what population you're talking about really doesn't matter when it comes to the general ideas. So you could be talking about bacteria, or you can be talking about people, or you can be talking about frogs or rabbits or deer, or even plants or cyanobacteria. So it really doesn't matter what the population is. Its size and how it changes over time is determined by very, very specific factors, very specific key abiotic and biotic factors that really are more logical than you might think, and they're, in my estimation, fairly obvious if you just give it some thought. So can you think of 3 things that might define how big the size of a population is? Think about it for a second and see if you can name 3 of them. Take a pause the video and write them down. Well, the 3 things are really broken down into 2 things, and it's really kind of straightforward. And that's that a total population, if you have a population, let's say, let's put it in a box, and let's put 5 triangles in a box. And what's going to determine the change in the number of triangles over time is how many are coming in versus how many are going out of that population. That seems pretty straightforward. In versus out. Now, what determines what comes in and what comes out of a population? Well, obviously, one of the things that living systems do is give birth, right? So giving birth is definitely something that you want to take a look at. So the little baby triangles are going to be born. How many of those are born over time? That's called the birth rate. So part of the in is going to be the birth rate. But as we know, if you've been watching the news at all, triangles can also come into a population, right? In the case of human beings, we've seen a lot of immigration, a lot of discussion of immigration in politics. But in any population over time, you can have immigration coming into that population. So maybe you have 10 deer in a forest. So some deer from a neighboring forest could come and enter that area and become part of that population. But of course, we have to consider, so that's in, so it's birth rate plus the immigration rate, right? And as we discussed when we discussed Hardy-Weinberg, immigration is individuals coming into a population. Best seen really among humans, because we tend to migrate, either immigrate or emigrate all the time. And so going out of a population, obviously if birth rate's going in, then death rate has to be what you consider going out. Right? So that's simple. I think everyone can understand that. And when we're talking about, instead of immigration, when individuals leave a population, if any individual triangle decides to leave this population, that would be called emigration. So those two together would be the out part of the equation, right? So it's just really simple. The word again comes to mind, common sense. We've discussed how little of that there really is. But logically, that makes sense, right? So if you have a total, the amount coming in minus the amount going out gives you your total population in a given system, the system defined by whatever it is that you're looking at. You define the system. So in this case, it's this box, and the population are these triangles, and the birth rate is how many of these triangles over a year, let's say, and immigration is how many of these triangles come into the population from outside over that year. Add those two together, and you have your in, right, your in part of the equation. If you think about the out part, and again, it makes sense that over time, any triangle might die, an accident or old age or disease or predation or any number of things. A meteor might hit it. So these out, so death rate is something to consider. How often do people or triangles die over the year, right? And of course, emigration triangles will move out of that population to go somewhere else for whatever reason. So death rate plus emigration is how many are going out. So that any change in a population in its most basic form is considering the birth rate and immigration minus the death rate and emigration. In other words, in minus out. And those two together give you the change in that population, right? All right. So let's go ahead and expand on that and think about what is it that really determines that death rate, or that death rate and birth rate. What influences these two? Well, before we do that, let's take a look at something called exponential growth. And exponential growth is really when you have ideal conditions. So, for instance, you have virtually unlimited space, and you virtually have unlimited food supply, unlimited water, unlimited oxygen. So think of all your resources. You can have as many as you have, and there's going to be as the maximum number of new babies being born. So you have to maximize your in and minimize your out, right? And if you're maximizing in and minimizing out, you're going to get this just boom of growth. So 1 gets you 2. 1 goes to 2, which then goes to 4, which doesn't go to 8, right? But actually goes to 16, which then goes to 256. But that's only if you're talking about the population squared. That means that if each individual has in a year, let's say, has just doubles. So each one individual has 2. But what if the exponent isn't 2? What if it's 4 or 5? What if puppies, dogs have in any given litter might have 5 or even 6 puppies. Mice can have 4 or 5 or 6 pups, right? Of course, you'd have to divide those by half because you have a male and a female involved in giving birth. But let's just go ahead and think about this and just say, what if the exponent wasn't 2? What if it was 4? Well, 1 would then get you 4, right? So if the exponent were 4, then you'd have 1 going to 4, going to 256, going to 4,294,967,296. So you can see that would be a very quick and speedy increase in the graph. So what you would see then is what we call an exponential curve. So that means that the curve would go straight up like so, where you just start with 1 and then maybe you hit 4 and then here you're at 256 and then all of a sudden you're all the way up here at 4 billion, right? Plus. So that's that would be an exponential curve, a very steep curve that goes upwards. There's negative exponents, but let's just think more right now about a change that's an exponential change, not a doubling, not times 3, but some x to some kind of exponent. Okay. So this is kind of unlimited growth, right? And it's easy to think about this kind of growth when you're talking about, for instance, a petri dish where you put a bacterial colony in the center, and then you come back, and the bacterial colony has gotten a little bigger, and come back leave it over the weekend, and the bacterial colony has actually gotten a lot larger, and here you're having this kind of exponential growth. You started with a couple or few, and you started to increase that growth very quickly. That's called exponential growth. Very fast growth over time. And if you can imagine in a petri dish, as you let it go over time, the bacterial colonies would just keep multiplying to some amazing amount. And it's much easier to think about unlimited growth for bacteria because they're so small and the planet's so large. But exponential growth in nature really doesn't happen, because at some point, even for this bacterial colony, which is up in the trillions by the time it gets to the edge of the petri dish, they've reached the edge of the petri dish. The nutrients are running out inside the medium, inside the agar. The nutrients are running out. The space itself is running out. And they're starting to produce the waste. They're starting to produce a lot of waste because there's so many of them. So you have a lot of waste. You have low nutrients and limited space are going to lead to an increase out, right? An increased death rate. And you're going to decrease the growth rate. You're not going to be going at 4 or 2. You're not going to be going at x to the second power. You're going to be going a lot less because there's not enough food for it to grow at that rate. So this exponential growth rate doesn't really occur in nature for a long time. This exponential growth rate happens initially. So if you think of a long period of time, in the very beginning of the growing period, so going back to what the petri dish looked like at first, when you first put that colony in the center of the petri dish, at first it had virtually unlimited space, virtually unlimited resources. So it could go at an exponential rate. So it could grow very quickly. But soon as the space started running out, as the nutrients started running out, the growth rate had to slow down, because what's going to slow down the growth rate is you're going to have larger death rates, a lot more going out, and the birth rate itself, in this not birth because this is a binary fission, but the binary fission rate itself is going to slow down. Now this is going to be applicable to humans. It's going to be applicable to any organism, because the same factors, the same influences are happening no matter what the organism or what the population is that you're looking at. So what determines a population size? Why is it that a population cannot be an infinite size? Why can't a population be an infinite size? Well, as we said, there's resources. Resources are limited. There is no infinite resource. There's no infinite fresh water resource. There's no infinite land. There's no infinite food source. There's always going to be some limit that you're going to reach, and that limit is going to be determined by the situation that you're looking at, by the size of the environment, by the size and the need of the individual and the need of the population. Of course, also you're going to be limited by how many predators there are in the area, right? What the disease rate is, how many prey are there. So this would be the food supply. This would be what's eating you, and these diseases are the things that would also kill you. So this would be this would influence out, right? And this would also influence how fast you can come in. If there's not enough space, air, water, or light, then there's not going to be enough room for anyone to be born. So there's this concept that you have both abiotic and biotic factors that limit how far the population can grow. So an ecosystem can support a maximum number of individuals in the population. That maximum is different for every species and ecosystem. That maximum is defined by the abiotic and biotic factors that exist in the ecosystem and changes as the ecosystem changes. That maximum is called the carrying capacity. So the maximum an ecosystem can support is called the carrying capacity. Now, what's interesting here to me is this second point, right? And that's that the maximum is different for every species and every ecosystem. So if you have a species A in this system, let's call it box 1, and species A has a specific carrying capacity. Let's say it can carry 5. It can hold 5 individuals without a problem. But in box 2, maybe it has more food. There's a larger food supply in box 2. Or there's more water, there's more air. Or box 2 is just bigger. So maybe instead of having just 5, limited to 5, maybe box 2 can hold 10. So that's the concept of carrying capacity. Here you have the same species, but the environment's different. This environment can hold, box 2 can hold more, where box 1 can hold less. Now, if you think about it, the same thing applies. If you have the same box 1, maybe it's the same kind of box as somewhere else. And the boxes are representing ecosystems, right? So there's a box is just a system. So maybe in species A is very tiny, like a bacteria. And the box 1 for can hold billions of bacteria. But it can only hold 4 deer. So the bacteria, billions might be an underestimate, was certainly underestimating the number of bacteria. Maybe I should say trillions. But the point being that the size of the organism, the need of the nutrients, how much nutrient does it need, how much space does it need, how much oxygen does it need, what are the resources that each individual bacteria needs? Not as many as the deer, because of all the things that bacteria is small, and because it eats very little and needs very little resources for each individual bacteria. You can have a lot more bacteria in the same box, the same ecosystem. So the characteristics of the species and the characteristic of the ecosystem are both important to trying to understand the carrying capacity. How much can an ecosystem hold of any given population? How many, I should say. So let's think of a fishbowl as an ecosystem, and instead of a box. And if you had a fishbowl, there's a limited amount of space and food and oxygen. If you have 3 in a fishbowl, the fish are happy. If you overpopulate the fishbowl quickly gets increases the rate of disease increases. Oxygen starts running out. The food starts running out. No oxygen, no cellular respiration. Remember that. And of course, space is running out. So the individuals will get more aggressive and start tearing at each other. So you can see that this population has gone above and beyond its carrying capacity. And so the result is death, increased outgoing. So what are the types of limits what are the types of concepts of considerations you have to take in when you're talking about things that limit a population, that limit it either in its birth rate, for instance, in immigration, or in its out, meaning the death rate or its emigration. What limits this population from growing? And there's 2 basic kinds of limits, and those that are dependent on density. So in other words, density dependent limits are limits that uh, would would be impacted by how many individuals you have. So food, for instance, would be dependent on how many you have. If you have 50 people and one cake, that limits how much cake each individual can have. And again, I think it's common sense, right? So how much food there is dependent. How much the carrying capacities, the food supplies, if impact on the carrying capacity, is dependent on the density or how many individuals you have. Where something, another thing that's density dependent would be something like space, how much space you have. But what are some of the density independent factors? Things that are not dependent on how many individuals you have. Weather, how much does it rain? How much sunlight do you get? That really won't be impacted by how many individuals you have. It can be depending on what you're talking about. If you think about a rainforest, the more individuals you have, the less sunlight's going to reach the bottom layer of the rainforest. But at the canopy level, the number of individuals that exist at the canopy level, the number of leaves, for instance, or the number of trees, that's not impacted, or that won't be the amount of sunlight is not impacted by that, right? So so that's something you should consider when you're talking about density independent and density dependent factors. Let's look at some of the things that are not dependent on population size, and some of the things that are dependent on population size, and that influence how much an ecosystem can hold, how many individuals an ecosystem can hold. So a population size can be impacted by human disturbance. Now, that won't matter if you only have 2 deer or if you have 100 deer. You destroy their habitat, the population size is going to come down. So a disturbance by humans, in whatever way that disturbance comes, is going to impact the population size, and it doesn't matter what the population size is. A natural disaster like a volcano erupting, an earthquake, a tornado, a hurricane, those are weather as well, but a meteor hitting the earth, whatever happens, these natural disasters, they can impact the population size. And again, it doesn't matter how many you have in the population, there will be a major decrease in that population size. Climate is, again, not dependent on how many individuals you have in that population. So these three are going to influence the population size, or they're going to limit the population size, and it won't matter what the population size is. They're going to be able to change that population size. So, an example of climate. Let's think about it. So, you get an average rainfall of 3 inches. 3 inches a day, let's say in an area. If the climate changes, and now you only have a half an inch per day rainfall, then the population size is going to be impacted. Was that change dependent on how many individuals you had in the population at the time that the change occurred, right? When the rain stopped coming so frequently? The answer is no, right? So the population size really did not determine the impact of the climate change, or it did not determine the climate change, the natural disaster, or the human disturbance. Now, how many individuals you have in the population predation does depend on how many individuals you have, because the more you have in a population, the more predators can eat, right? Parasitism is another form, something else that's really dependent on how many you have in a population. The more you have in a population, the more parasites you can have. Disease spreads quicker when there's a more dense population. The competition for living space, obviously, if you try to pack 100 fish in a fish bowl, you're going to have a lot of competition for living space. Food competition, how much food there is. Obviously, if you have 3 fish versus 100 fish, there's going to be a lot more competition for that food. Competition for water resources. Again, thinking about those fish, those 3 fish that are by themselves in the fishbowl have a lot less to worry about than those 100 in that same in a similar space. So these are all density dependent. They're dependent on density, right? So if you have 3 fish, now if those 3 fish, if a natural disaster happened and the fishbowl broke, it wouldn't matter if there were 3 fish or there's 100 fish. There's going to be a negative impact on. There's going to be a major limiting factor on the growth of those fish. So you see, natural disaster doesn't have anything to do with how many fish are in that fishbowl. If that water gets really, really hot and they all die, it doesn't matter if there's 100 or there's 3. They're all going to die. So again, there's that limiting factor that does not depend on how many fish are in that fishbowl. But if you think about parasites or disease or predators or competing for space or competing for food or competing for water, then I think you can see that how many are in that fishbowl are going to have is going to be determine the intensity and the impact of these factors. All right. Now we're going to be talking about S-shaped curves, and we're going to be looking a little more on what kinds of graphs are impacted, what kinds of changes happen in graphs when you're looking at populations. So let's take a look at graphing carrying capacity. So if you had, in a population size, and this is kind of a boom or bust. So here's a boom where the population is having a really, really big growth spurt, obviously exponential, right? And here's a bust. So here the population size went way above the capacity. This is the carrying capacity, by the way, right here. The capacity in that environment to hold them, to support them. So you can imagine back to that fishbowl example. Those fish went from 3 fish down here to 100 fish up here. Well, what's going to happen is really quickly. Almost as quickly as they grew, they're going to sink. They're going to die. Individuals are going to die. There's not going to be enough room to have babies, so you're not going to be able to bring many more in. But there's a lot going out, so you have this bottom until finally there's been enough death that you have more space, you have more food. Things start bouncing back. Things start looking better, and you start to grow again. And now you have you reach another limit, another max. So your first max is pretty high, and then you reach another max, and of course you start to come down again. Maybe you're running out of food this time, or water and space, and you didn't have as many. You had you had a stable population to begin with, but now you're starting to lose more than you're gaining. Your out is bigger than you're in. And so now you're below the carrying capacity, which means now you have more space to grow. Again, you still have more food than you do individuals. You have more space than you have individuals. You have more of resources in general than individuals. So again, the population starts to increase again. And you'll notice that what happens is that you get this kind of first initial big jump, and then it just starts to ease on into what we would call homeostasis. Now this line shows kind of a flat line here, and really in nature it doesn't ever really get flat. It just gets real small, and it kind of stays that way. And there's going to be seasonal fluctuations. There's going to be chance fluctuations, things like disease spreading or what have you. So rarely are you going to get a population that just stays at carrying capacity perfectly. In fact, that probably doesn't happen in nature at all. You're just going to have constant fluctuations. Something to think about when you're talking about the population size, and notice that that's what's on the Y, over time, is not just that it fluctuates up and down around some homeostatic point, which would be called the carrying capacity. That's the ability of the environment to sustain a population, right? So not only are you going to get this up and down, but there's going to be a lag. There's going to be a lag in the change in the population as the environment changes. So if you have an increase in, let's say you have an increase in predators, and so you get, instead of 2 wolves, you have 20 wolves now hunting. Well, that would be a response to having so many prey. Well, what would occur is that the wolves would come in, and of course, having that many prey, they can have more babies. The babies could survive more. You quickly go up to 20 wolves, and what happens is that starts to decrease the wolves, but or the prey. So the prey starts to decrease. But now you have 20 wolves. Maybe you're up to 30 now, and now your prey are really low. Well, your wolves are going to start to decrease at this point, and as because your prey are decreasing, the number of wolves are going to decrease, and so you have this kind of lag that happens in the changes. So this change in population size doesn't happen right away. There's an impact on the birth rate. There's an impact on the death rate, and that impact, it takes time to see it in nature, right? So how does a population show an increase and then a decrease over time? Why does the population show an increase and decrease over time? And that again has to do with the ability of the environment, their prey, their water supply, their air supply, their space to adapt to the various populations as they go up and down. They're dying. As they go below the carrying capacity, they can increase again. As they go above it, they start to die off again, and finally they just kind of stay at their carrying capacity. The dotted line represents the carrying capacity. So let's take a look at the idea that when we're looking at animal populations, there could be seasonal changes. So as we're looking at winter, right? There's this kind of baseline population of the geese, of the pheasant, of the rabbits, and of the deer. Of course, what are these animals? One would have to call them prey animals, right? And so as we get into spring, they have a lot of babies. Duck might have, you've seen them with their little ducklings, maybe 5, 6, 7 little ducklings following them along. Pheasants might have the same number. Rabbits are famous for having a lot of babies. A deer might have 1 or 2 for each breeding pair. So these, probably just 1. They're pretty big babies. So the increase in the population in spring is a great deal. Like there's a big increase in the number of animals in a population in the spring. Come summer, they start to decrease. Now, why is that? Well, in the spring you had all those babies born, but now when we start to get to summer, the babies are getting larger. The food supply is getting smaller, right? So there's starvation going on because there's so many babies. They're eating all the plants, and they're drinking all the fresh water. And so you have a lot of disease. The more animals you have together, huddled together, there's more disease, and parasites are spreading. So these are density dependent factors, right? There's accidents happening. So that's part of the outgoing, the death. Weather changes, the drought, or temperatures too hot, or too much rain, flooding, can all impact the death rate. As now all the births happened over here, so that's why you have this giant increase really quickly. But over time, over the season, over the summer and going in through autumn, what you're getting is a lower and lower number of individuals in the population. If you think about deer, you see there's always in the spring, you have all the young deer that you see as your parents are driving. You're looking at deer crossing the road. Come the end of the summer and into autumn, a lot of those deer got hit by cars. They were hunted by coyotes. They starved to death. So a large number of them died, and you're back down to some really base level of population that has back to the normal carrying capacity of that environment, of that ecosystem. Now with deer, because we've gotten rid of their predators, right? Deer have overpopulated. They've stayed at their seasonal highs. And we've actually had to increase hunting. We call it a cull, or culling them. And we have to kill more of them than a hunter would normally kill so that we can bring that population down again. Why would we want to do that? Because if we don't, then they can overeat the vegetation, which would reduce other organisms that depend on that vegetation, like pheasants and rabbits and such. Also, they would increase in disease. They would starve. There'd be a lot more starvation. So because there are no predators for deer, natural predators for deer in our area, hunting then has to take a bigger role in controlling the population of deer. But this seasonal kind of surplus and sinking is part of that up undulating line that you saw around the carrying capacity. Now let's test you on whether you understood the concepts, right? So you have this number of rabbits, and this is in May. So this is the beginning of spring, right? In June, there's this giant increase. Well, what happened here? Well, parents were starting to breed, right? The rabbits are starting to breed, and then here the rabbits are starting to be born. There's more and more rabbits until you get to some level at this point a carrying capacity. This is logarithmic growth, and there's your exponential growth here. So this logarithmic growth is a growth that just is kind of curves easily, slowly across to some limit, right? And here in an exponential growth, you have this growth that's very steep and very quick. So when you're looking at an exponential growth, again, you're looking at a growth that shoots up, and you can see that growth can be defined pretty much around this area, right? Let me increase the size of the pen here. Pretty much that exponential growth can be identified here. So that's the exponential growth part of this population curve, and that happens in the spring, and that's when you're having a lot of resources relative to the population, and so you have a lot of room for the population to grow. And this now in a logarithmic growth, what you see is kind of a slowdown of the curve, kind of going up at first, but then just kind of easily curving down to some kind of a limit, and that limit is the carrying capacity in this case. That's the ability. That's the line. That's the number. So let's see here would be about what 65, right? So that would be about 65 rabbits. Would this environment can hold about 65 rabbits. That's the limit. It can't hold anymore. If it tried to hold more, if for some whatever reason some rabbits were very enthusiastic and try to have a lot of babies, then something, whether it be predators or disease or starvation or lack of water or space, would start to bring it down. And once it went below the carrying capacity, it would have more food and room and what have you, and it would come right back up again. So in nature, the curve would look more like this, where it's going up and down. However, in kind of our estimations and our predictions, we like to look at things as either exponential or logarithmic, and we can then helps us predict this region, this area that we would call the carrying capacity, where this undulation of the population, or increase and decrease of the population, would occur around this carrying capacity here. So do you understand? Do you understand what this curve shows? So let's say that this is a curve shows a population going toward the carrying capacity. What would happen if the deer's food supply was destroyed? Instead of rabbits, if this were deer, number of deer, what would happen if the deer's food supply were destroyed? And some kind of wildfire or disease or the drought, what would happen to that population? Well, it would come down. And if it's completely destroyed, there's no way for them to recover, then they would all die. And we call this extinction, right? So that's extinction. when every one of the population, well, it would be the whole species would just die because it just doesn't have enough food, or they're whatever the situation, or space, or whatever the situation is. Another example is if a particular species only lived in this forest, and a developer wanted to develop that forest, let's say owls, right, or sheep, or whatever. This one species needs this space to be able to breed, because this is the environment that has all the necessary resources. And you, as a developer, come in and want to build a mall there, or condos, or whatever. When you do that, you disrupt that environment, so they have no place to live, no space to live, no place to eat, no place to drink. So they're all going to die, and that's causes extinction. That's a bust. So they had a boom, right, and then they had a bust. They had a zero. They went down to zero. That's a collapse. That's a population collapse, which can happen. But more likely, what would happen is if in nature you had the disease or the lack of food would happen, you'd have a decrease. But then as you got less and less deer, rabbits, or what have you, there'd be more food available. Over time, the plants would be able to recover and grow more fruit, or what have you. And the deer would then be able to increase. But then as you got too far above that carrying capacity, the plants again would there wouldn't be enough food or water, what have you, so they'd have to come back down, and we'd go back up and back down, and it would just keep going around that center, that line, that 65, that carrying capacity about 65 in the case of the rabbits, or deer, or whatever it is you're looking at. So let's take a look at this flowchart. I got some of these off presentation online. So let's take a look at this and see how we might be able to fill this in. So if we are looking at carrying capacity, right? So if we're saying that carrying capacity would be here, well, what's carrying capacity determined by? What's determined by limiting factors, right? Well, what limiting factors? Well, food, space, and water are certainly three big limiting factors. So food, space, and water. And so above the carrying capacity, we'd expect the population to decrease, right? Why? Because the population is larger than the capacity of the environment to sustain that population. So you'd expect the population to decrease. Below that carrying capacity, again, looking at that line where you have kind of a beginning growth, exponential growth, and kind of logarithmic growth, the carrying capacity would be here, right? So too far above that line, if the population went too far above that line, you'd expect there to be a decrease, right? If you went too far below it, you'd expect there to be an increase. That's the point there. So population decrease, and below it you'd see a population. You'd expect to see a population size increase, right? So that's how I would use these vocabulary words and this word bank to fill in this flowchart. All right. So hopefully you understand that concept. So in summary, an environment can only support as many organisms as there is available food, water, and free space. Carrying capacity is the maximum number of organisms that can live in an ecosystem based on these limiting factors. We can read the population growth curve to predict changes in population size. Below carrying capacity, you expect the population to increase in size. Above the carrying capacity, you expect the population to decrease in size. Again, because remember, the carrying capacity is the ability for that ecosystem to support that population. If the population goes above it, that carrying capacity, then that ecosystem cannot support it for whatever reason, whatever limiting resource is stopping them, you're going to see a decrease in that population. And over time, population stabilizes at a carrying capacity, but always undulating, always moving up and down. It's just the ups and downs are not as extreme as it was at the beginning. So you'll have a large up, large down, and then they'll start to get smaller and smaller. But there's always going to be changes. Sometimes seasonally, sometimes it's never constant. So remember that it goes back to that concept of dynamic equilibrium, right? Where you're getting, even though you're pretty much at this carrying capacity, you're always getting some changes back and forth. All right, so let's move in. All right, move on. What are 3 limiting factors that determine the carrying capacity of a population in an ecosystem, right? What is happening to the population at point A in the graph, and why? There's point A. What's happening to it? What's happening to the population at point B and why? What is the carrying capacity of population based on this graph? So you should be able to answer these based on this video. If not, rewind it and think about it. I expect these due on Friday, and I'll write it in the Jupiter Grade message. By Friday, I mean not this Friday, which is the spring break Friday, but the following Friday, right? It'll be after your exam, so you'll have a whole week to try to get these answers. You should have them before Thursday, because Thursday you're getting your major exam, but the questions won't be due till Friday. I would turn them in as quickly as I could if I were you. Questions due, again, some more questions due by Friday. You look at this graph. When did the rabbits reach carrying capacity? About what time or what month? How do you know? How do you know that the rabbits reached carrying capacity? What is happening to the population during the month of June, right? And while you're at it, what's happening in that population, and describe it in as much detail as you can. Use some of the vocabulary words I used here in this video. What are some potential factors that could limit the rabbit population? So think about it. And you know what? Break that out a little bit. Think about this. Answer this question. What are some factors that limit the population, but what are some density dependent factors that are going to limit it? And be specific. And what are some density independent? So answer those two, make a list, and of course, again, those will be due by Friday of the following week, not this Friday, next Friday, April 7th, I believe it is. So your objectives, define carrying capacity and identify limiting factors. I hope we've done that. And they contribute the carrying capacity of population, for population. Predict changes in a population size based on limiting factors and carrying capacity in an ecosystem. And interpret the growth curve of a population. I hope you can do that. And to see if you can do that, I'm going to ask you to do this. Again, due by Friday. Graph the rabbit growth rate. Use this data and put it on the X. When the X, put generations. And the number of rabbits, put it on the Y, right? And graph it and see where the carrying capacity is. Tell me in what generation do you see exponential growth? At what generation do you see logarithmic growth? What is the carrying capacity? So answer those 3 questions. Where is there logarithmic growth? Again, review the video if you have any questions. And then 3, where carrying capacity. Where is the carrying capacity? What is it? How many rabbits can this ecosystem support? All right. So hopefully, again, by Friday, you should be able to discuss the results of your graph, answer those questions and explain it. What trends you see, how does the graph change, and answer those 3 questions. I think you'll be able to answer that. That should answer the first bullet point here. Did the population reach carrying capacity? Why or why not? If it didn't reach carrying capacity, why didn't it? If so, indicate when the population reaches carrying capacity, indicate the maximum number of individuals can be supported. And that again is another one of the questions I asked you a moment ago. What factors are responsible for the rapid growth trend? So think about the factors, again, density dependent, density independent factors that would either explain its quick growth or quick death or whatever's going on. If a predator like a fox or a cat, which often prey on rabbits, were introduced to the environment during the 10th generation, now that's the 10th generation, what would happen to the population? Explain your answer. So again, think about that. What would happen at the 10th, if you introduced a predator at the 10th generation, what would happen? If I were you, I would think about drawing, making a copy of that graph, a digital copy, and thinking what would occur if I added a predator to this population at the 10th generation. Why is the 10th generation so important? All right, so that's it. I hope this video helps you understand what carrying capacity is. The work is due next Friday. I will go over it with you in class, any questions you might have. So that gives us, Monday we have a test, Tuesday, and knowing that some of you have an exam, pro core quality core exam in geometry. I think it's on Tuesday. It might be on Wednesday. Whatever day you have, I'll be there after school next week as well. So good luck on going over this material, and I hope it all makes sense, because it is, if you think about it, it all is pretty much a logical sequence of events.